Welcome to today's explainer. Look, if you're used to coloring basic commodity plastics, you might think the exact same formula works everywhere. But as we're diving into today's material, we're finding out that's definitely not the case. We're stepping completely away from the safe, low-temperature world of basic plastics and jumping right into the extreme, high-heat world of engineering plastics. It's a totally different game, guys. The stakes are higher, the processing conditions are absolutely brutal, and honestly, using the wrong pigment here doesn't just mean a slightly off color, it means total part failure. Let's get right into it. So, here's our roadmap for today. We'll start with the high temperature challenge, go over the rules for pigment selection, break down some polymer-specific strategies, walk through a real-world troubleshooting case study, and finally, wrap up with the professional R&D mindset. Part 1. The High Temperature Challenge. To really understand why this heat is such a massive hurdle, we kind of have to shatter the illusion of standard plastic processing. We aren't just making simple, everyday containers here. Engineering plastics, materials like ABS, polycarbonate, and nylon, are utilized for high-performance applications. We're talking about heavy-duty automotive components right beneath the hood, delicate electrical connectors, LED housings, and complex consumer electronics. And because these parts literally need to endure extreme stress out in the real world, they require extreme high-temperature processing conditions just to be molded in the first place. Just think about these processing temperatures for a second and what we're truly up against. ABS? That runs between 220 and 250 degrees Celsius. Nylon can easily push up to 300 degrees. And polycarbonate, or PC, can demand a staggering 320 degrees Celsius. Now, imagine taking a standard pigment that's only stable up to 220 degrees and just tossing it into a polycarbonate melt at 320. The pigment won't just shift, it will be completely obliterated. The result is fading, burning, severe yellowing of the polymer, and, well, immediate rejection by your customer. No way around it. Moving on to Part 2, Rules for Pigment Selection. What's really fascinating here is the massive paradigm shift required. You see, a basic pigment check usually involves just picking a color because it has a beautiful, bright visual shade. Simple, right? But an engineering pigment check is more like a rigorous interrogation. You literally have to verify heat stability, light fastness, weather and UV resistance, chemical resistance, and absolute polymer compatibility. For instance, if you're molding an outdoor automotive part, and you pick a pigment solely based on how bright it looks, completely ignoring UV stability, well, that part is going to heavily fade within months under the sun. It's a guaranteed failure. Part 3. Polymer-specific strategies. First up is ABS. On the surface, ABS is a total joy to work with. It offers this beautiful high gloss and is generally really easy to color. But man, it's surprising how quickly a plastic with such a gorgeous gloss can turn incredibly ugly if mishandled. Its main challenge is that it's highly prone to yellowing and developing burn marks if you push it too hard. So the pro tip here, you absolutely must use heat-stable organic pigments. If you try to cut corners on pigment quality with ABS, the material will punish you with dark streaks and a really nasty burnt appearance. Next is polycarbonate, the heavy hitter. It's naturally transparent and super tough, but as we saw just a minute ago, it requires massive heat, up to 320 degrees Celsius. Now, aside from a natural tendency for a yellow shift at those crazy temperatures, its absolute biggest enemy is moisture. If you try to process polycarbonate without properly removing moisture first, this fascinating but highly destructive chemical reaction happens. The trapped water rapidly expands into steam during processing, causing silver streaks and bubble marks everywhere. Because of this, pre-drying the material is absolutely compulsory. Skipping the drying process, that's a fatal mistake that will ruin your entire batch. Then we have nylon, or PA. I want you to think of nylon as a notoriously thirsty sponge. It absolutely loves to absorb moisture right out of the atmosphere. The tricky part is that this moisture absorption drastically changes how the final color presents itself. If you aren't careful, you're going to experience severe color variation from batch to batch simply based on the humidity in the room. So, the golden rule for nylon is to always compare your dry material with a fully conditioned sample so you can see the true final color. Finally, we have PBT. Engineers love PBT for its incredible dimensional stability. It just holds its precise shape beautifully. But there's a catch. It is highly vulnerable to high-temperature degradation. So to maintain that precise shape without breaking down the polymer chains, using strictly heat-resistant pigments is completely non-negotiable. It really goes to show every plastic truly has its own strict rulebook. All right, part 4. Troubleshooting and case study. So let's look at what happens when these rules get broken on the factory floor. It turns out almost none of these common defects are entirely the pigment's fault. Look at yellowing. That's usually caused by the machine temperature being way too high, the plastic sitting in the barrel too long, or maybe a poor stabilizer. Shade variation, often caused by moisture or processing fluctuations. Black specks? Yeah, that's burnt polymer from dead spots in your machine's barrel, or honestly, just poor cleaning between runs. And surface streaks typically point to low mixing or poor dispersion. You might be standing there thinking the pigment is bad, but it turns out the machine is literally baking it alive. It's so frequently a processing failure, not a color failure. Let's actually walk through a real-world detective story to prove this. Step 1, the complaint comes in. A customer is furious because their pristine gray ABS part is turning a sickly yellow. Naturally, they assume you sold them a faulty, cheap pigment. Step 2, the investigation. You go in, run the tests, and find out the pigment is perfectly fine. The real culprit? The operator had set the machine barrel temperature 20 degrees Celsius above the recommended limits for that specific ABS grade. The plastic was literally baking. Step 3, the solution. You optimize the temperature, reduce the time the plastic spends inside the machine, and boom, the trial is repeated and the final part is perfectly gray and approved. Just goes to show, sometimes the machine, not the color matcher, is the real culprit.
Part 5, the professional R&D mindset.
To operate successfully in this high-stakes space, we really have to be proactive. According to the research, there are 5 absolutely crucial questions that must be answered before a single pigment is even touched. So, how would you prepare? Well, here they are. Question 1. What is the exact polymer grade? Not just, oh, it's ABS, but which specific grade? Question 2. What is the exact processing temperature the factory will actually use? Question 3. Is this part living indoors on a desk or outdoors taking a brutal beating from the sun and rain? Question 4. What's the required gloss level? And finally, question 5. What is the expected lifespan of this product? Is it a quick disposable item or a 10-year automotive component? Only after you have the concrete answers to these 5 questions can you safely decide on a pigment formulation. And mastering all these basics sets us up perfectly for where we're heading next. In our upcoming explainer, we are going to dive into the incredibly fun and complex world of special effect masterbatches. We'll be exploring exactly how to achieve pearl, metallic, fluorescent, marble, and even glitter effects, all without compromising the integrity of the plastic. It really comes down to this. Successful color matching and engineering plastics isn't just about the pigment. It's about deep polymer knowledge and absolute process control. Which kind of makes you wonder, right? The next time a colored plastic part fails in your hands, was it the recipe that was flawed or the machine that molded it? Keep experimenting and I'll catch you in the next explainer.
Before you leave, I want you to remember one thing. Color matching in engineering plastic is never just about adding pigment and getting the right shade. Anyone can make a color look perfect on the first day, but the real challenge begins when that same color has to survive high processing temperature, demanding application, harsh environment, and years of product life. Think about it. Why does a perfect ABS set suddenly turn yellow after molding? Why does PC color shift after multiple processing recycles? Why does nylon produce unexpected shade variation because of moisture? Why does PBT sometimes give a completely different appearance even though the formulation hasn't changed? These are not a random problem. These are the real engineering challenge that separate on an operator from a color matching expert and an expert from a R&D specialty. In today's video, you have learned the fundamental, but this is only begin. In the next episode, we will go even deeper into the science behind engineering plastic. I will show you how professional color matcher select heat stability pigment, predict color shipped before production, solve molding defect, reduce costly rejection, and develop formulation that remain constant from the first batch to the thousandth batch. These are the techniques that are really taught in classroom and are usually learned only after years factory experience. So if you are serious about building your career in plastic technology, color matching, master batch development, or polymer R&D, don't miss the next video. Subscribe to the channel, turn on the notification bell, and become part of this learning journey, because step by step, day by day, we are not just learning color matching. We are learning how real polymer engineer thinking, troubleshooting, and innovate. I will see you in the next video. Thank you.